Swayam Prabha. Digital India. Educated India.
Welcome to week 7 of our NPTEL course on Muffler Acoustics. Here we have application to automotive exhaust systems. Now, in this week what we are going to do, week 7, we are going to for the first time introduce the effect of mean flow on the acoustic performance of mufflers. And before we do that, actually it is a little bit involved topic, because now we are going to see the effect of mean flow on the perturbation quantity and how all these things are going to affect the muffler performance. So, what we need to do first is that we need to sort of develop new variables called aeroacoustic state variables, and before even we do that, what we need to do is basically consider some expressions for the acoustic intensity due to flow in a pipe when we consider the mean flow effect. So, let us see how we do it. What we will do is that the flow, that is, let us say m being the rate at which the flow occurs, mass flow rate in a long pipe, something like this. So, we have velocity u can actually vary small u over the cross section. So, we can write u as u r. So, this can be written as rho naught times u r 2 pi r dr, all right. So, where this is over S and S is your pi r naught square. Okay. So, now typically when you have flow over ducts, we have a profile, let us denote the mean flow Mach number, which is a function of radius as u bar by c naught, where u bar as a function of r is nothing but your average velocity, and typically this is usually taken as m naught times r naught minus r by r naught whole to the power 1 by 7. So, basically this expression, what it does, it gives us a good idea about how the Mach number varies over the cross section radius r, and taking into account the effect of boundary layers and all that. So, this is typically valid for fully developed turbulent flows at the Reynolds number of the order typically 10 to the power 5 or 1/10 or something like that. This is typical in internal combustion engine, exhaust pipes of internal combustion engines, and what we have also observed that the average value of the Mach number is typically about 0.85 times Mach number observed at the right at the center. So, the flow profile will be something like, if I allow me to draw an exaggerated view. So, it will be something like this sort of a thing, this. So, here we are talking about m naught here. So, here we have average Mach number I am talking about is something like AVG, you can refer to that, 0.85 times m naught. Now, what about expression for the average acoustic intensity for the waves that flow in a moving media? So, let us denote this by Ni be the average, or let us say Ni be the intensity over a small elemental area ds when you have, this is a circular part. So, something like this. So, Ni ds, something like this. So, we have this kind of a thing, E is equal to Ni ds. Now, basically we have this. So, Ni is the nothing but the instantaneous energy flux that is normal to the surface element. Okay. We have that sort of a thing. We can write this Ni as enthalpy times Mi, okay, where Mi is the mass flow rate and J being the enthalpy. So, what we do is basically put energy as integral over the cross section area J times Mi into dsi, where I really means some ith element in a big complicated muffler. There is nothing very sacred about the number I, and j is the stagnation enthalpy, that is the flow where to be very gradually brought down to rest. So, this is your enthalpy, and plus let us say V, let us say V be the total fluid velocity. So, let me call this as V1, something like this. So, we have this sort of a thing. So, J is equal to H plus Vi square by 2, we have this, and the mass flow rate is nothing but density times volume velocity. So, this is nothing but rho us. So, when we combine these two things, we get this. So, enthalpy stagnation enthalpy, I would, let me write down this thing more clearly. Stagnation enthalpy is the sum total of the enthalpy of the flowing fluid plus the velocity head term, that is the flow where to be brought down to rest. And what about Mi? Mi is nothing but rho times Vi. So, we have really got two variables. Now, what we are interested in acoustics is really the perturbation quantities. So, how do we describe that, or how do you, let us first of all denote these perturbation quantities. So, we denote the perturbation quantities as J dash or J prime, you can say, and let us first also look at the volume velocity term. We can write this as the mean flow velocity, that is u naught, that is sort of an average velocity over the pipe, plus your perturbation acoustic velocity. So, this situation is something similar to like a person, you are observing the person on the ground and the train is sort of moving, and there is a passenger in the compartment. So, it is doing oscillation from one seat to another seat. So, you would still see a net movement of the particle or of the person, but it is also oscillating. So, that is sort of a situation. So, let us focus back on this equation. So, we have this sort of a situation then where Vi, or the, let me write it properly, Vi is sum total of your u naught, that is the mean flow velocity, and your small perturbation velocity. We also used to call it u tilde. So, I will sort of retain the same convention. So, what happens then to the perturbation stagnation enthalpy? So, you know, when you have a small perturbation over the ambient thing, then we can write this as J plus J dash is equal to H plus H dash plus half times u naught plus u tilde whole square. So, is equal to H plus H dash u naught square, something like this. So, this we can further write it like u naught square by 2 something like this. So, then we can sort of regroup the terms and write these guys as another thing that I want to point out, that u tilde being small, u tilde square will also be very small. So, we tend to sort of neglect that, as we have done in the first week of the course when I introduced these perturbation quantities and talked about how small they can be. So, the second order terms will be, you can neglect it with respect to the first order terms, and you can again sort of regroup this, and H dash plus your u naught and u tilde, something like this. And so, basically what we get after doing all this algebra is that we get J dash is nothing but H dash plus u into u tilde. So, we get this perturbation stagnation enthalpy. Similarly, we can also get the mass perturbation mass thing, and that is m dash. So, we can write this as nothing but rho naught plus rho tilde, remember, and this is your S cross section area u plus u tilde. So, if we were to systematically multiply the terms, so this is your average thing and this is your perturbation thing. So, u naught so again we will ignore this, and what we will do is this. Taking S common and rho naught u tilde rho tilde u naught. So, we have another relation between the perturbation mass flux. Is your m dash is equal to S times cross section times rho naught u tilde plus rho tilde u times u, and this is these things. So, I will rewrite this stagnation thing again, perturbation stagnation enthalpy, that is your H dash like this. Okay. So, this is what we get. Now, once we have these two quantities, so now it is a time when we go back to the expression for the, or probably rewrite the equation for the energy total acoustic power coming out of the duct carrying a mean flow as something like this. Average thing is S times J dash M dSi or the ith element. So, intensity clearly means is nothing but J dash times Mi dash, all right. So, we have this sort of a thing. So, what we need to do is basically, in order to develop an expression for the intensity that goes through the duct, acoustic power that goes through the duct, we will probably have to substitute equations 1 and 2 in equation 3. So, once we do that, we will get your after some algebra, I am going to sort of avoid doing that, we will do those things. So, we will get P dash and U tilde, and then we get U naught divided by rho naught and P tilde and rho tilde plus your U naught rho naught times square plus U naught square U into rho tilde, and this is of course this thing. So, here P dash and U dash will be in general functions of the radius. It is quite natural to get that, because pressure and velocity will both gradually have a variation over the cross section area. So, basically what we can do is that we can box this thing. So, this is the average time averaged acoustic intensity that goes out of the pipe, but then again I is a function of r, because these variables will depend on the radius. So, now in order to find out the total acoustic power that is radiated, so we just need to simply integrate the intensity over the cross section area. So, once we do that, we will get the following expression. So, we will get the expression which is your P and V, where V tilde is your, remember, mass velocity, and these things mean the time average. So, now we have taken the time average of these things, time average or RMS. And this is your nothing but this P tilde square plus my naught times V square So, here V, like I said, is the acoustic mass velocity and m is the space averaged or the mean flow number that is averaged over the duct cross section area, and y naught is your characteristic impedance. This is the total acoustic power time averaged. Remember, this is much more complicated, or it is more tedious, I would say, as compared to the case where the flow was not there. So, now as a check of self consistency, if you put m 0, that is, this term is not there, when you put m 0, no flow, then all these things will go away, and what you will be left is just this term. And if you recall, this is your acoustic power that is radiating out of the duct when there is no flow involved. So, now basically what we can do, one would naturally like to use this expression that is developed for the case of non-zero mean flow, and then put suitable assumptions, like let us say pressure field at a particular, we will put, typically we have things like k naught x plus b times a j k naught x and so on. So, here we will put x is equal to 0 or z is equal to 0, whatever suits us, and we have this, and your this velocity is nothing but a minus b by y, and we will assume that b by a is equal to r, meaning that reflected wave or backward propagating wave is reflection coefficient times the incident amplitude wave. Now, r is the reflection coefficient, which can be complex also. So, this can be complex quantity, much like your the progressive wave variables b and a. Okay. So, now once we substitute these two guys in the big expression that we sort of developed here, and I am going to sort of avoid the algebra and just work on, just present to you the final result of how it would look like. So, we will get the power acoustic power that is radiated over the duct as 1 by 2 rho naught times y naught 1 plus m square like this. So, we will get this sort of a thing. This is the expression for the total power radiated when you have non-zero mean flow. Clearly, when you have m is equal to 0, so this will and this should sort of reduce to the more familiar expression, that is your 2 rho naught times y naught times 1 minus mod of this thing. Now, if we just do some algebra, take a inside this thing, we will have mod a square minus mod of a into r whole square, that is nothing but b. So, this is something that we have seen in the very first few lectures of this course. So, let me box this expression. So, this is something that we kind of will be using when you want to develop the expression for the transmission loss in the presence of mean flow. So, let us do that now before we move ahead to the case of aeroacoustic state variables. Before that, we probably would like to make some comments on the non-zero Mach number. So, as we will see here from this particular expression, let me call this 3, this is 4, this guy is your 5. So, from 5 we get to see that Wm or the acoustic power radiated out of a duct which is carrying a non-zero mean flow, in general that is greater than the acoustic power radiated out of the duct when you do not have any mean flow at all. So, that is for all m, and the error that would be caused by neglecting the mean flow for a given reflection coefficient would be positive and more significant around mod r, which is approximately equal to 1 unity. Let us evaluate the expression for the maximum reflection coefficient R max. So, what we can do? So, R max, then as we can see, what does, let us revisit equation 5 and figure out what does this term mean. So, as we discussed just a while back, this thing probably means that the acoustic power that is carried by the wave that is going in the positive z direction or along the duct, as we can see, and then so this is what it is. And what about the wave that is traveling in the backward direction, that is in this thing. So, that is basically your this part into this, that is your this guy is multiplied by this. So, it has certain meaning. So, we will keep this thing aside for a minute and worry about the acoustic power incident, that is your mod A square by 2 rho naught y naught 1 plus m A square, and the one that is reflected is your A times 2 rho naught y naught r square 1 minus m square. Okay. So, we have this sort of a thing. Now, clearly reflection coefficient can be maximum only when the incident thing is equal to the reflected thing. That is, whatever in a duct carrying a mean flow, whatever acoustic power is being transported by a wave that is moving in the positive x direction, the same thing is being reflected back by the wave that goes along the negative x direction. So, when that will happen, so we have to really equate these two terms. So, when we do this, obviously your this will cancel and so will this, resulting in your 1 plus m whole square is equal to r mod r square times 1 minus m whole square. So, this is your maximum reflection coefficient, maximum because I just explained the physical significance when this happens. Basically, you know, your entire acoustic power that is being carried in the positive z direction is being reflected back. So, under such a situation, r mod square is equal to 1 plus m whole square 1 minus m whole square. So, basically this would mean r max is equal to 1 plus m divided by 1 minus m, all right. So, this is your maximum reflection coefficient. Now, clearly there are few interesting things I would like to talk about here. When m is 0, so r max can just be equal to 1 when m is 0, isn't it? We just said m is 0 and you will get reflection coefficient r mod maximum r that you can get is 1, and that is in consistency with our physical explanation that whatever acoustic power is being carried by the forward propagating wave, same the entire wave is being reflected back. So, reflection coefficient is 1. However, when you have a non-zero mean flow, that is m is non-zero, it can be some number, typically you know, in exhaust pipes it is about maximum is 0.3, 0.3 is really on the higher side, typically it is about 0.15, 0.2, and once it goes in the chamber because of expansion it is even smaller, although we would not really allow it to expand due to a number of reasons which we will discuss in this week's lecture. But all I am trying to say is that in the chamber it might be even lesser. So, under such a situation when you have a non-zero m, okay, so it can be even more, reflection coefficient can be more than 1, let us say it is about 0.2. So, we have basically 1.2 divided by 0.8. So, how much would that be? 3 by 2, that is about 1.5, reflection coefficient would be about 1.5. So, the point is here is that when you have a non-zero mean flow, it means that reflection coefficient in terms of the classical variables, classical progressive wave variables can be more than 1. But that is probably the reason why, due to a number of all these things, it is a good idea to introduce some kind of a new variables which are more suited for aeroacoustic analysis, and we will refer to them as aeroacoustic state variables. We will worry about all those things in the next set of lectures. So, or next class probably, but what we can do now is just develop in the remaining time some expression for the transmission loss. So, we saw from our, I think from our week 4 or 5, I guess probably week 4, I reckon week 4 we saw the transmission loss expression in terms of the 4 pole parameters, that is you have your system, you know, P1 and V1 as T11, T12, T21, T22, you have this sort of a thing, isn't it? So, if you have a system which is being characterized like this, I would say 1, 2, okay. The transmission loss then is given by TL is nothing but 20 times log 10, and your element, this can be your y2, y1 root over that. So, we have this. And here we have this sort of a thing, isn't it? This is for the case when you have no mean flow, that is 0 mean flow. But however, you like to extend all these arguments to the case when you have a non-zero mean flow, that is M is something like whatever we get typically in a automotive muffler. So, let us make use of our understanding for the using the expression that we just developed now for the acoustic power carried by the wave when you have a non-zero flow. So, let us say when we have a system, it can be any complicated muffler system. So, if we have an inlet port here, outlet port here 2, and in the classical state variables, that is P1, V1, P2, V2, the system is still characterized by this sort of a representation. Okay. But here you also have mean flow. In the inlet pipe, let the mean flow be M1 and here it will be M2. So, it is pretty straightforward to see that the acoustic power that is carried by the incident wave variable, that is the wave that goes in this direction, is nothing but this term. So, we will write this as W incident is equal to A, or I would say A1 square by 2 rho naught y 1 plus M1 whole square. We will have this sort of a thing, and the one that is incident, that is going in this direction, is that is basically transmitted, is basically your one plus M2 whole square, isn't it? This is the only thing that you need to worry about. A1 and A2 can be figured out from this thing when you substitute back the classical variables A1 minus B1 by Y1 and all these things here, and same thing over here. So, basically once you do that, we will put these two expressions in the transmission laws, and let us see how the expression for transmission laws here is modified. This is given by we will put 1 plus M1 and 1 plus M2 times all the big expression that we just mentioned here, this entire thing. So, I am not going to write it here. So, you can also have a look at the book by Professor Munjal in the 3rd chapter, where all these derivations are given in a greater detail. So, the point is that in the presence of mean flow, expression for transmission laws will be pretty much the same, barring the fact that there will be additional terms due to mean flow present in this thing. So, naturally one corollary that happens, that occurs, is that when the Mach number is same in both the pipes, which can be the case when the pipe has the same diameters. So, then you have this term basically goes away and you get back the classical expression for transmission laws. So, now I guess I will stop here in this lecture, and in the next class, class 2 of week 7, what we will do is that we will introduce for the first time aeroacoustic state variables. So, M dash and J dash is what we talked about, and obtain expression for acoustic intensity in presence of non-zero mean flow. So, what if we basically do some manipulation of the terms, we will see that we can probably relate M dash and J dash in terms of the classical variables, but then you have presence of mean flow. M terms, Mach number terms will be there, and we will develop some again expression for the acoustic power radiated and carried by the forward moving wave, and that carried by the backward moving wave and all that, and possibly talk about transfer matrices for tubular elements or extend inlet outlet elements, and do all those sort of things. So, that will be the focus of the next lecture or something like that. Thanks, stay tuned.